Hello everyone, my name is Jiang, and I'm very glad to have this opportunity to share with you some of our recent research. COMET, a novel memory-efficient deep learning training framework by using error-bounded lossy compression. So first of all, let's look at some of the biggest challenges in training deep neural networks nowadays. On the right upper side, this figure demonstrates that today we use larger, deeper neural networks for higher accuracy and for higher reliability, but this will cause a very high memory consumption. And also, in most of the cases, you also want to use a larger batch size for training, for higher conversion speed, and for higher resource utilization. And another thing is the limited GPU memory space. So although NVIDIA has released some of the GPUs that is specifically designed for deep learning purposes with large memory space, it's still not comparable to CPU memory, and it's still not enough for especially scientific models. And on the right bottom side, this figure is illustrate the typical process of a training phase. So you can see there is forward phase and backward phase. In the forward phase, activation data will be generated and will be stored somewhere, and it will be only used until the backward phase hit the same layer and will be used to compute the gradient and then update the weights. So you can see this will cause a big gap between the activation data being generated and being stored to being used in the backpropagation. Some of the previous solutions meaning has three categories. One is migration between CPU and GPU. So this has some limitation because of the I/O throughput, and also it requires very comprehensive scheduling design for the migration. And also recomputation, so basically to recompute the layer before the backpropagation hit the same layer. But this is not applicable for convolutional layer because convolutional layer is hard to recompute, and it will introduce a very high overhead. The third one is that some study has used image-based compression, the JPEG, to compress this kind of activation data, but it results in a relatively low compression ratio because JPEG is not designed for this kind of data, and it's also designed for integers instead of for floating point numbers. So the principle of our solution is to compress the activation data after it's been generated and keep it in GPU memory and decompress it when needed in backpropagation. Actually, NVIDIA is also interested in implementing such lossy compression to deep learning frameworks, and we are discussing with them to see the collaboration and implementation possibilities recently. So for lossy compression that we use is that it's compressed the data with little information loss in the reconstructed data. However, it can provide a very high compression ratio, typically over 10 times. This is especially helpful when compared to lossless compression, which is typically less than 2 times in this kind of application. And nowadays, the new generation of lossy compressor can provide controllable compression error to control the compression data quality. So two types of the lossy compression out there. One is transformed-based lossy compression, such as ZFP, and another is prediction-based lossy compression. So the principle of that is to use surrounding data to predict the next value and to enhance the encoding efficiency, such as SC. So we use prediction-based lossy compression in this case because it outperforms the ZFP specifically for this use case. So previously, this kind of lossy compression is used for reduced storage overhead and to improve I/O performance for scientific applications. And this would be the first work to use this kind of lossy compression to reduce memory consumption for deep learning purposes. And some of the challenges includes that one is that the continuous zero in the data will need to be specially handled. Otherwise, it will affect the training performance. Another is that we need to understand how the introduced error will propagate throughout the whole training process. And the third one is to balance between the compression ratio and accuracy. So we do not want to sacrifice any accuracy. However, we do want to provide as high compression ratio as possible. So here you can see this is an overview design of our framework. This figure is basically a zoom in of one of the previous figures. Left-hand side is the forward phase, right-hand side is the backward phase. So our framework mainly has 4 phases. The first one is parameter collection. So we collect some of the parameters, for example, from activation data. We collect the sparsity of the activation data. So those collected parameters will be used for two assessment, gradient assessment and activation assessment. So the gradient assessment will estimate the acceptable variance in the gradient that will not affect the accuracy. And then using that result, we do the activation assessment to estimate the acceptable error that can be introduced for compressing the activation data. And then with that result, the error that we can introduce, we can then use that to adaptively compress the activation data. And you can see in the figure, after we compress the data, we wait until the backpropagation hit the same layer, and then we decompress the data for computing the gradient, and etc. So more specifically here, we can see start with is the parameter collection. So there are two types of parameters that we will be used in our research. One is offline parameters. This can be collected before training. The other is semi-online parameters. So we call it semi-online instead of online is because that during our evaluation, we find that if we can collect all those parameters every iteration, but the result, the configuration based on those parameters will not change dramatically between each iterations. So what we do is that we collect those parameters every 1,000 iterations to reduce the frequency of those parameter collection and to reduce some of the overhead. So we call it semi-online parameter collection. And that includes activation data sparsity, average loss, average momentum value. And then using that, we do the gradient assessment. So here I will jump through some of the theoretical analysis, and if you are interested, please check our paper. So we have a very thorough theoretical analysis, especially for activation assessment. So for gradient assessment, the result is that we conclude we will use the variance that is within 1% of the momentum average. And then using that, the activation assessment, the first thing we do is to do error distribution estimation with lossy compression. So it turns out we use uniform distribution, and because in this application the compression ratio is typically within 20 times. If it's beyond 20 times, there is some other distribution that we may use, but in this case we use uniform distribution. And use that, we build a model for gradient error distribution estimation, and the result will be a normal distribution. And on the right hand side, this is a demonstration that we collected during our evaluation. You can see all the layers, the error distribution is normal, is a normal distribution as expected and as our estimated. So if we do this computation backwards, then we can compute the error bound based on the acceptable variance that we calculate for the gradient. You can see this equation here uses some of the offline parameters, some of the online parameters such as the activation disparity, and also the gradient assessment to compute the error bound, and then further to use it for compression configuration. And the next step is adaptive compression. As mentioned, the compression configuration will update it every 1,000 iterations based on the semi-online parameter collection. And then we need to modify the CoolSE, which is a cooled down version of SE for GPUs, to compress the sparse data. So actually the activation data is not that sparse, but it will contain continuous zero. And typically for SE lossy compression, sometimes we will compress those continuous zero into a continuous small values, and this will cause loss explosion, and the training will fail without any modification to the compressor. So after modification, we can compress, so the zero will remain zero after the lossy compression. So next step, let's look at the evaluation. So we have evaluated our framework on 5 models, 2 datasets, 2 frameworks, and 2 platforms. And a brief view on the error impact evaluation is that on the left-hand side, this figure is that where we try to identify the acceptable variance for the gradient. So essentially, we chose 1%. So you can see if we choose 2%, there will be too many accuracy degradation. On the right-hand side is to demonstrate our accurate theoretical prediction to the gradient error distribution. You can see the real distribution and the predicted distribution matches with each other pretty well. And next is to use our framework for the models. So you can see on the left-hand side, we show the accuracy curve compared with the original and our framework. So you can see they match with each other. So this means that even though we can provide a very high compression ratio by up to 13.5 times, we introduce very little or no accuracy loss to the model itself. So on the right hand side, you can see this is a chart that demonstrates some of the compression ratio from our models. You can see the lowest compression ratio is still over 10 times. And compared with image-based compressor like JPEG, it's a big improvement. And in terms of the performance, so first of all, let's look at the right bottom side. This figure is a comparison between our solution to migration and recomputation. So you can see our solution provides the lowest compression, lowest overhead among all the three solutions. And this is very beneficial for our end-to-end performance improvement. And the second one is the raw performance improvement. So because we compress the data, we can actually use larger batch size, and larger batch size typically will result in a higher GPU resource utilization. And on the right upper side, you can see the raw performance image per second will be improved. And the third one is end-to-end performance improvement. So because we use large batch size, we can actually improve the conversion speed, and also because of the raw performance improvement, the end-to-end improvement can be up to 2 times, as demonstrated in the left-hand side figure. And also noted here is that because our framework is applied to each node and each GPUs, so there's no communication needed, so it has high scalability for it. So lastly, let's look at the conclusions. So we propose a novel memory efficient Sian training framework via dynamically compressing the intermediate activation data through the error-bounded lossy compression. And in this work, we provide a throughout theoretical analysis for the compression error propagation during training process. And using that, we propose adaptively configured error-bounded lossy compression techniques to compress these data. And during which we also improved the SE lossy compression to handle the continuous zeros to avoid some of the training failures that we encountered in our experiments. The evaluation results shows that our framework can provide an up to 13.5 times data reduction for memory consumption and up to 1.8 improvement compared to the best previous state-of-the-art method. And for the end-to-end training performance, we can improve it by up to 2 times. And some of the future works include that first, we want to integrate this with migration and recomputation. So this method is not perfect. So for example, it does not work well when the convolutional kernel is 1 by 1. In that case, recomputation may be a better solution. And for very deep neural networks, maybe migration will be better for some of the layers. So we would like to see what the performance would look like if we hybrid all those three types of data reduction techniques. And the second one is that we want to explore this solution to other types of layers and models. So here we mainly focus on the convolutional neural networks. We will also want to see how it performs on other models like transformers. The third one is that we want to reduce the compression and decompression overhead. So we actually have a very deep connection to the developer team of CUDA-SE, the CUDA version of SE. So we are working on some of the high throughput compressors while has very little impact to the compression ratio. And yeah, that's all. Thank you.